Yo, 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 your boy is back in his house. Today, I want to talk to you about a little something called bioaccumulation and biomagnification. Two different topics that are very closely related. And it all connects to these questions below. What happens when toxic pollutants enter an ecosystem, particularly an aquatic one? How do they impact the organisms living there? And oddly enough, why shouldn't young kids eat tuna fish? This and more tonight at 5. Sorry, I'm not a news channel, but I'm auditioning, so I thought I'd practice. Anyway, moving on. Take a look at this. This connects to that question about tuna fish. Pause the video and read it. Think about it for a sec. This picture is all about consuming responsibly tuna fish. It's not alcohol or vaping or Monster Energy drink. Why are kids not allowed to eat too much tuna fish per month? 4 times a month? What? Is this ridiculous? Okay, this is America. My kids should be allowed to eat whatever they damn please. Stop telling me what they can and can't eat. Well, angry mom, it's not meant to be a sort of restriction in terms of your rights so much as it is a health concern. If you look at what the mercury levels in tuna is up there with one of the, in terms of fish that we actually eat, because we don't really eat some of these higher fish here. But if you look at the x-axis, this is mercury content, and on the y-axis are different types of fish. Tuna are some of the worst offenders in terms of the concentration of mercury per ounce. This is right on the border of the type of fish that you want to avoid eating due to mercury buildup. And if you're wondering why is mercury bad, well, it leads to mercury poisoning, which leads to a whole variety of issues regarding anxiety and reproductive health, nervous system, circulatory health, memory problems, skin rashes, etc. The Mad Hatter from Alice in Wonderland, the reason that he's referred to as the Mad Hatter is because back in the day when this story was originally written, hats were often made using mercury. And so the people who would sell them, hatters, would go crazy due to mercury poisoning. And so they were called Mad Hatters, which is where this whole guy gets his whole thing from. So mercury is not so great. And this is too much tuna. There's too much tuna there. There's mercury in there, and it's going to poison you if you eat too much of it. Yay. Now, I'm not trying to be alarmist here. I'm not saying tuna fish is bad, but if we go back to this diagram, right, for young kids who have weaker immune systems and smaller bodies, eating too much tuna a month can lead to buildup of mercury within the system, within the body system, which can lead to mercury poisoning, potentially, right? So you might be wondering, angry mom, why the tuna is even in your, or why the mercury is even in your tuna to begin with. Well, let me explain it to you. Well, first of all, it's not actually mercury. It's a little something called methyl mercury. When mercury is deposited into an aquatic ecosystem, bacteria will convert it into methyl mercury, which is highly toxic. This is the chemical formula. You can see there's mercury in it, but there's also a methyl group, carbon and 3 hydrogen. So first of all, it's not mercury, it's methyl mercury. Okay, sure. So why is there methyl mercury in tuna fish? Well, it really comes down to the two topics for today's lesson. Bioaccumulation, which is this notion that over time a toxic substance will build up in the organic tissue of an organism. The fancy definition is as follows: the selective absorption and concentration of elements or compounds by cells in a living organism, most commonly fat-soluble compounds. Yes, thank you, Encyclopedia Britannica. Bioaccumulation is one reason, right? Mercury will build up in the tissue of tuna over time, but additionally, there's this concept of biomagnification, which is that, well, not only is it building up in the tuna, but it's building up, the mercury is building up in the tissue of the prey that the tuna eat, and in the tissue of the prey of the tuna. Meaning that as you go up in the higher trophic levels, the buildup of that toxin is going to become more exponentially. Or, if we go back to our encyclopedia friend, the increase in concentration of substances per unit of body tissue that occurs in successively higher trophic levels of a food chain or perhaps in a food web. Yes, thank you, Queen Elizabeth, for those wonderful remarks on what biomagnification is all about. Words are one thing. Let's look at a picture. That will surely set things straight. This is bioaccumulation. The idea that in a dolphin or a fish or whatever the heck this is supposed to be, over time, the contaminant levels, whether it's mercury or anything else, is going to build up in their body tissue over time, just because of repeated exposure over their lifetime. Biomagnification, on the other hand, is the idea that, well, a little bit of buildup in shrimp, well, if you've got dolphin that eat a lot of shrimp, all of that buildup that's in the shrimp is going to end up transferring to the dolphin. And you've got a seal that eats a lot of dolphin or fish. I think those are fish, because seals don't eat dolphins, and I'm pretty sure that's a fish. Anyway, if you've got like a moderate level of buildup in the fish, well, the seals are going to eat quite a few fish, and it's going to result in a pretty high buildup in the seals. And what eats seals but polar bears? So polar bears are going to have even a higher concentration of toxic buildup inside their system, right? So basically what we see with biomagnification is that organisms at the top of the food chain, apex predators and top carnivores, are going to be most impacted by this, right? We will see this in class when we do our activity. Here's another image describing the difference between the two. Bioaccumulation is the buildup of a contaminant like mercury in an organism's lifetime over time, whereas biomagnification is the successive buildup of that toxin through the trophic level, right? One bird needs 4 caterpillars. One snake needs 3 birds. One eagle needs 3 snakes. So those toxins are going to build up inside of the higher trophic levels very, very rapidly. So, what's the deal with tuna? Circling back, full circle. Tuna have a very high trophic level, right? Plankton have very low levels of mercury due to bioaccumulation, right? Like phytoplankton. Zooplankton, animal plankton, will eat those phytoplankton and build up a little bit more of that mercury. Small fish will eat those zooplankton and build up a slightly higher concentration of mercury. So now we're from a low concentration to a medium concentration. Larger fish like mackerel will eat those smaller fish, building up even more so a higher level of mercury in the tissue. And finally, tuna will eat all those larger fish like the mackerel and end up with a very, very high concentration of mercury in their system. So, because tuna have such a high trophic level, they have high levels of mercury due to both biomagnification as well as bioaccumulation, which is why you don't want to eat too much tuna in general, but particularly as a child, because it might lead to mercury poisoning. It's not just tuna, though, and it's not just mercury. It's any toxin, any pollutant that is what we refer to as persistent, a persistent organic pollutant, better known as a POP, meaning that it hangs around for a while in the ecosystem. And when I say POP, I don't mean what you're probably thinking of, a cheery grandfather or a glass of Coca-Cola. No, I'm not talking about those. I'm talking about persistent organic pollutants. Persistent organic pollutants, like I said, they're persistent. They hang around for a while. They don't break down easily, not in the presence of acid or sun or wind or whatever. They hang around because they're synthetic and they're organic. They're carbon-based, so they don't get broken down very easily. Many organisms will absorb them, and the body systems don't know what to do with them, so they just build up in fatty tissue, right? Going hand in hand with that, they're often soluble in fat, meaning they sort of dissolve or merge with fat very easily, which allows them to accumulate inside the fat tissue. Now, a little bit of POPs might not be bad, but if it builds up in the fatty tissue, it can lead to toxic levels through bioaccumulation. And lastly, POPs can be carried by wind or rain and travel long distances, much like acid rain, far from the initial source, which can mean that they can get deposited somewhere very far away from where they were initially created, such as at a factory, and can get deposited miles away in an aquatic ecosystem. Let's talk about some examples of persistent organic pollutants that aren't mercury. DDT, something that we mentioned way back in Unit 5 when we learned about pesticides. It causes cancer, meaning it's carcinogenic. And it much like other POPs that biomagnify, it's going to affect top carnivores, most notably the peregrine falcons and other large predatory birds end up with thin eggshells, reproductive malformities, and developmental deformities due to the buildup of this carcinogen inside of their body. Luckily, it was banned in 1972 thanks to Rachel Carson's bombshell of a book that exposed the dangers of DDT to the world. Another example are some things called Pcbs, also known as polychlorinated biphenyls. I have a friend of mine in college who studied these, and they're pretty dangerous. They're used as an industrial coolant. They were banned in 1978, but they banned from being produced in 1978, I should say, but they're still pretty much widely used, even though they're not being created anymore, and they can, again, lead to cancer. Interesting fact, if we think about CERCLA, the act that monitors Superfund sites and cleans up abandoned hazardous waste sites, many of those abandoned hazardous waste sites are releasing PCBs into aquatic ecosystems. The last one that I'll mention are called PFAS, or C8. This is another carcinogen. No matter who you test around the world, whether in China, Africa, Europe, the United States, or hell, even Antarctica, they have PFAS in their blood. They are called forever chemicals. They do not break down. They are found in things like nonstick pans like Teflon or Gore-Tex on your Patagonia. And they can build up in the blood and lead to severe birth defects as well as cancer, thyroid disease, high cholesterol, you name it. One of the documentaries you may end up watching over spring break called The Devil We Know, it details this whole cover-up by DuPont, which is the chemical manufacturer. Thrilling documentary. PFAS are found all around the world. They've been detected in water sources all around the country, particularly at industrial sites, airports, wastewater treatment plants, and military training areas. There are PFAS in the water that you drink, as you will see if you haven't already from the test that we do in class. The issue with PFAS is that they are found in packaging. Anything that is resistant to water or wax or oil probably has PFAS in it, and those things get either put in the landfills, which then end up in the environment or crops, or they get, like if it's on your, say, your pan or your cookie bag or whatever, it's going to end up in your food, which you will then ingest. So one way or another, it's going to end up in our blood, in the blood of organisms in the ecosystem, as well as the tissue of things that don't have blood, like plants. All right, let's pause real quick. So far, we've talked this unit a lot about different types of pollutants, and I just want to clear up some of the categories. We've talked about sources of pollutants. Oh, sorry, I'm going to edit this right now. That should say not primary versus secondary, but point versus non-point pollutants. A little bit behind the scenes there. We've learned about the different sources of pollutants, a point source versus a non-point source. We've learned about the effects of different pollutants, such as it being an endocrine disruptor or a carcinogen. And now we've learned about the persistence of pollutants, most notably persistent organic pollutants. Keep in mind that these categories can and will overlap. Don't confuse them, though, because they're talking about different things. Last thing I want to leave you on is, thankfully, the Stockholm Convention in 2004 is an international treaty designed to limit and even eliminate the use of persistent organic pollutants in chemical manufacturing around the world, which is fantastic, and they've done a wonderful job of that. Take a look at this map, which shows the countries that have signed the treaty. Any country that is green has signed the treaty. If you have not looked at the map, just look at the United States. Notice the United States is not green. Apparently, it's not easy being green. Goodbye.